Okay, today we study ESA5H, scalar product, and Pythagoras theorem. The area of a parallelogram spanned by A and B. Let me draw a parallelogram spanned by two vectors A and B. So A is, if I choose this starting point to be the origin and the head of this vector, small a, is capital A, and then this one is B, then I can draw a parallelogram spanned by these two vectors A and B. So, parallelogram OACB, OACB. Okay, parallelogram, two sides are parallel. I mean, these two vectors are the same, and these two vectors are the same. Okay, in that case, we have a parallelogram spanned by two vectors, small a and small b. The area of a parallelogram is magnitude of A multiplied by the height of this parallelogram. Height of the parallelogram. So magnitude of A is absolute value of A, and magnitude of B is this, and then height of this parallelogram is, if I define this angle between A and B to be theta, then this is a B absolute value sine theta. Therefore, the area of this parallelogram is B absolute value multiplied by sine theta, where theta is the angle between A and B. Okay. So these two vectors can be expressed as a linear combination of three Cartesian unit basis vectors. They are E1 hat, E2 hat, and E3 hat. And A1, A2, A3 are components of this vector. Okay, for example, A1 can be expressed as a scalar product with the E1 hat and vector A. We know if I multiply the scalar product of E1 hat, these two contribution vanishes, only the first one survive. So in this manner, 1, 1, 2, 2, and 3, 3. So for I equals 1, 2, and 3, any Cartesian component can be expressed as a scalar product between this vector A and the unit Cartesian basis vector. In a similar manner, I can express the vector B in this way. Okay, and then if I draw a parallelogram, the angle between A and B is always can be chosen such that the angle theta is between 0 and pi only. Okay? Therefore, sine theta, that is used to determine the height of this parallelogram, is a positive definite. We recall that scalar product of A and B vector is A times B times cosine theta. From this, I can define cosine theta. I can determine cosine theta as a scalar product of A and B divided by the product of the magnitudes of the two vectors. If I can determine the cosine theta using the scalar product, I can substitute this one in this formula. This identity determines the sine theta, and this sine theta can be substituted to find the area of this parallelogram. As I explained, scalar product is a product of the magnitude of the two vectors multiplied by cosine theta, and the area of a parallelogram spanned by A and B vectors is a magnitude products A absolute value, B absolute value, square root sine theta. And this sine theta is square root 1 minus cosine theta. And using this identity, we can express the area of the parallelogram completely in terms of square of A, square of B, and the scalar product of A and B. We further simplify this expression by making use of Cartesian coordinates. According to the Cartesian basis vector, square of any vector is the sum of the squares of the Cartesian coordinates. So a squared is a1 squared, a2 squared, a3 squared. B squared is b1 squared, b2 squared, and b3 squared. Scalar product of two vectors, we have vanishing off diagonal components and only diagonal components 1, 1, 2, 2, 3, 3. All right, I can make use of these three identities, substituting these values for a squared, b squared, and a dot b, a squared, b squared, a dot b in this area formula for the parallelogram. After that, what I have to do is expand this product and expand this square. In general, a plus b plus c multiplied by b plus x plus y plus z can be found as by applying the distributive law. That means we have a x plus y plus z, and b x plus y plus z, and c x plus y plus z, and add them all together. So this is the answer. Using this formula, I can expand the product of square of vector A and square of vector B. A little bit tedious, but it is straightforward to find the answers for this expansion. Okay, I hope you can do it yourself. And then, next step, I can square this. It is even simpler than the previous product expansion formula because this x, y, z are the same as a, b, and c respectively. The result is a squared, b squared, c squared, and 2 times a times b, and 2 times b times c, and c times a. The reason why we have factor of 2 multiplicity factor is that we have an expansion of ab and ba, and because of the commutative law, these two products are identical to each other. Therefore, because we want to know this scalar product's square, I can substitute a1, b1 in here, a2, b2 for b, and a3, b3 for c to find the final results for the second term. So complete expansion of these two lead to this, inside the square root of the area formula, we have this expression. We find the exact cancellation of these three pairs. And then finally, we find that A1, B2, A A2B1, A1B2, A2B1. But the crossing term A1, B2, A2, B1, they are crossing term. So these three terms can be combined to make a complete square. Okay, we can complete the square of the remaining four terms. Remaining six terms. 1, 3, 3, 1, 1, 3, 3, 1. So they construct a square, and the remaining three terms, 2, 3, 3, 2, 2, 3, 2, 3, 3, 2. So these three terms construct the squared expression. Okay, so what we have made use is these three identities. Finally, the area of a parallelogram spanned by two vectors A and B is found to be square root of product of magnitude square of these two vectors subtracted by A dot B squared. That is exactly the same as the square root of the sum of these squares. Sum of these squares. Okay, so it is straightforward to define a special vector that is perpendicular to both A and B. The reason why we say this A cross B is perpendicular to both A and B is as it is. For example, what about this? A1, B2, A2, B1, and A1, A2, B1, B2, but this is a B2 or B1 and negative sign. For example, okay, E1 hat, E2 hat plus E1 hat, E2 hat, no. So 1, 2, 2, 1, 1, 2, 2, 1, this term. Let us consider this term only. If I multiply the A1 dot to this A cross B, what we find is A1, A2, B3, A3, B2. A2, A3, B2, B1, A1, B3, A3, A1, B2 minus A2, B1. And we have to sum everything together. Let's see. A1, A2, B3. A1, A2, B3. I can find A1, A2, B3, but with the negative sign. This one cancels exactly. A1, A3, B2. We have negative sign. A1, A3, B2. But we have positive sign. So this one and this one cancel. A2, A3, B1. A2, A3, B1. We have the same term, but we have different opposite sign. So these two terms cancel. Therefore, scalar product of A cross B, which is defined like that, with the vector A is exactly 0. This one means this cross product is perpendicular to the vector A. In a similar manner, if I multiply b dot to this a cross b, then it is also 0. Therefore, we find that area of a parallelogram spanned by A and B has the magnitude of this vector called the cross product of the two vectors. And the magnitude is nothing but the A times B times sine theta, where theta is the angle between the two vectors. And the direction of the vector represented by the cross product A cross B is always perpendicular to both A and B. The angle between A and B is theta. We find the component vector B parallel, that is a component of B parallel to A. Let's find it. First, we define the unit vector A hat, that is the unit vector parallel to A. Okay, projection of B onto A. Okay, we have A and B, and we have a B vector and angle theta. The projection is this, the right angle, and we have the B magnitude. Projection is a B cosine theta. And the direction of A vector is A hat. Therefore, B parallel, that is the projection vector, component vector of B parallel to A, can be expressed in this manner, because this is nothing but A hat dot B vector. Okay. We can always decompose B vector into a sum of these two perpendicular vectors. We have B vector, I have some A vector, and then I have a projection. This is a projection along the direction of A hat. And what is that? This is this one plus this one is a B. Okay, we say this is a B perp, and this is a B parallel. B perp plus a B parallel equals a B. That means a B perp is a B subtracted by B parallel. Okay, in this manner, B is the sum of two perpendicular vector. This is right angle. These are two perpendicular vector, and perp direction vector. But perp component can be obtained by subtracting the parallel component relative to a vector A from original vector B. We find that scalar product between the two vectors is 0 because regardless of the magnitude of these two vectors, the angle between the two vectors is just a right angle. As a result, the magnitude of A vector can be expressed as square root of a square of that vector. We know the square of this sum of this parallel and perpendicular components leads to the expansion formula. Because parallel and perpendicular components are perpendicular to each other, this guy is absolutely 0. Therefore, the magnitude of a vector is the square root of a component parallel to a fixed direction and square of perpendicular direction. If I square both sides, so B squared is a B parallel squared plus b perp squared. This is nothing but the Pythagoras theorem. That's it for today. Thank you.